What's up, guys? This is Physics 2212 Lab 4 bar magnets. So here's the table of contents. We're going to have an introduction, go over the physics principles, the experiment procedure, look at the on-axis data and calculations, and then the off-axis data analysis. And then we're going to have a computational model for the off-axis, and then we're going to look at some assumptions and source of error, some observations, and finish up with some discussion questions and a conclusion. So the purpose of this lab was to measure the distance-dependent magnetic fields of a bar magnet, and then compare experimental data to a model using Biot-Savart law for both on-axis and off-axis. So our physics principles for this one are going to be Biot-Savart law, and then magnetic field of a dipole, and then distance dependence formula. And then the outcome is going to actually be that our n constant here is going to be that number, and our magnetic dipole moment is going to be this amount. So the basic principles, we have Biot-Savart law, that's this equation over here, and it's just a classic magnetic field at a point relating that. So we've seen that class. And then for our magnetic field of a dipole, this is the general formula. In our case, since we're going to be doing some on perpendicular and some parallel, we will be able to use different equations that are a lot more simple. This is the general equation which we will use in the code. And then distance dependence formula, this is given to us in this lab. But basically, for a bar magnet, it's equal to this number k, r to the n. But what we're going to end up doing is linearizing this later. So we can more easily solve these numbers, and it gives us a much more simple, so it'll be way similar. So for our procedure, we just took a phone, we downloaded a little app on it, so we could measure this. And what you had to do is first find where the spot was, where the magnetometer was. It's like right above the camera. And then we would measure from side to side. You pull this closer and further. The system was the bar magnet, and then, no, I misspelled that. And then the surroundings was everything else. So here's our analysis. So as you can see, it's a straight line here because we linearized it. So we put in all our numbers, all these different distances, and what we ended up getting here are these numbers, which we're going to take to our calculations. So here's our y equation, right? In this case, n is actually this number, and then natural log of k is going to be the y-intercept. So we have our b bar, and then we also know that b dipole parallel, in this case it was parallel with the magnet, is equal to 2 mu. And we're looking for this mu right here. This one, not mu naught, because this is constant. So our equations, we're going to set them equal to each other. And then what we can do is, so kr equals this. When we solve this around, what you're going to get is this constant here, kr to the n, this r3, this is the same r, so this adds to 3, divide by this 2, and you're going to end up getting that, imagine that's a mu right there. So when we calculate this out, we get 0.77 meters squared. Then we have our off-axis data. It did all this for us. All we really had to do is take the distance and then do some correction for the Earth. What we end up getting is this is our B net and our distance here. Now, since it was turned, because we're off-axis, you had to do the square. So you end up getting I think this number is square root 2. And here's the computational model. So put in our number that we got for this. We had to make a dipole way to solve for that. So we have to take our mag, we have our hat, and then we just this is that equation I showed earlier. Just put all those numbers in, and then our perp here, that's our average distance. So see, it's that number times square root 2. And then we end up plugging everything in. So what you see here, this is the 45-degree angle, which is this angle right here. And then this is r on axis, and then this is our off axis. So, or our perp, parallel perp. So we end up getting these numbers. They're a little different from what we got on the other one, but there are some reasons for that, which we'll talk about right here. So we're assuming that the bar magnet acts as a magnetic dipole perfectly, and that the field falls off perfectly with distance in this linear fashion. And then errors are that, so the Earth can extremely skew this data, right? So the phone, you're supposed to line it up perfectly. We did do that, but of course we didn't do it perfectly. Like the numbers it's impossible to do perfectly. So the code is doing that perfectly, and in real life it's not. And then the exact location of the magnometer may be incorrect. So here's some quick observations. So when the magnometer is far away from the magnet, it measures it near zero in the instruction. That's true, but it's really far away. It doesn't really have any effect. However, when it moves closer to the magnet, the next component, no, when you move closer to the magnet, it actually increases. So that's what this one is down here, right? As we move closer, it increases. So this one's true, this one is false. And then this one is that the position has no effect on the measured exponent. That is incorrect. So because we know this falls off with distance. So for our discussion questions, what if you hadn't oriented your experiment to compensate for the magnetic north and hadn't laid it out? So what if we hadn't even tried? It would have been so off. Earth would have skewed that number by an incredible amount. And then what if you were to stick two identical magnets together in two end? So that would just, the direction would remain the same, right? But the magnitude would double of those. So in conclusion, waves of magnetic fields, they interact with surrounding objects differently than the electric field. They act in an orthogonal way. Using Grove's law, we can calculate these fields. You must be careful to account for their magnetic field. Code can be used to simulate these fields, and it's a lot more perfect than a real-world lab. And you can linearize the data to make it easier to solve for magnetic fields.